All right, ladies and gentlemen, we are on student activity sheet 5. This is topic 4. With this is we talked about non-constant rates on the last section, but this time there's going to be a little bit more about those non-constant rates. So let's take a look at this first part. We got Dylan. He builds some homes. For him, completing one house takes him 200 days of labor. So he decides to figure out how much it's going to take, whether he's got 5 workers, 1 worker himself, or like 50 workers. Okay. So the first thing that we're going to take note of is that for him, one person takes 200 days. Okay. One person takes 200 days. So what we're going to do is we're going to go ahead and assume that if there were 2 workers, it would take 100 days. Split it in half. 4 workers would take 50 days. Split that in half again. And we would say we're going to keep splitting that. Again, like 2 workers, split that in half. We're dividing the 200 by 2 to get 100. If we have 4 workers, we took the 200 divided by 4 to get 50. Okay. So what we're going to do is we're going to get this full thing here, guys. So we got 8 workers. It's going to take 25, and so on and so forth. So what I want us to do, I want us to go ahead and graph this. Now, I know this isn't perfect, guys. It's going to be close. I know that 2 is less than 5, and that's, well, first of all, I know that if it's just me with 1 worker, it's way up here at 200 days. I know that if there's 2 of us, it's going to take us 100 days. If there's 4 of us, it's going to take us 50 days. If there is 8 of us, it's about 25. 10 of us takes 20. And then all of a sudden, 20 takes 10. And then lastly, 40, that's supposed to be only 5 days. Okay. I know it's kind of hard to tell, but I want to talk about what patterns we see here. What patterns do we see? The big thing that I notice, although ever so slightly, this graph is decreasing from left to right. Okay. My graph is decreasing. And what it's saying is as more people work, the less days are needed to work. Okay. So as I add more workers, it takes me a less amount of time to complete a job. Okay. So let's go on. Okay. Again, guys, this is what we talked about. The graph that we just had there. What they ask us is when the product of 2 quantities remains constant, what type of function does this model? Well, first of all, before we even get to that, I want to talk about, let's go back to our chart. What we noticed here, we know that it always takes 200 days total, and that's with like 1 person working. Okay, it's a 200-day process. So we figure 2 people working, that's 100 days for each person. Well, if we multiply those together, guys, that gives me the 200. If I do 4 people times 50 days working, again, that equals 200. What you'll notice for each of these, when you multiply them together, whether you're doing 2 to 100 or 40 to 5, it's always going to equal 200 days. Okay, 200 days. So the thing that I want us to note is the product. I think I kind of was a little repetitive. The product, take that off. The product is always constant. Okay. The product, if you guys remember what product means to multiply. So in this case, it was the size, the crew size times the number of days always equaled 200. And we call this inverse variation. Okay. Star that, highlight it. We're going to add this to our notes in a little bit. Inverse variation. And when we find that, what that is that's always going to be my x times my y is constant. My x times my y is constant. Okay, let's go on. Okay, now I am going to apologize. I thought I was doing something on this set and I got a little crazy and I didn't even need to do it. Okay, so let's look at this volunteer situation. Okay, look at the volunteers. Are my volunteers constant in this situation? Well, we go 2 to 4, 4 to 8, 8 to 10, and 20 to 4. I go up 2, up 4, up 6, up 10, up 20. So they're not constant. Okay. It's a big thing to note there. They are not constant. But if we come over here, let's look at my differences on this. From 100 to 50, that's negative 50, negative 25, negative 5, negative 10, negative 5. Again, guys, there's no real constant there. Okay. But so we would say that this rate of change is not constant. How can I tell just by looking at the graph? Well, look at the graph over here. I'm seeing that as the value of ratio decreased, okay, as the value of the ratio decreased, the steepness also decreased, meaning it became flatter. So as my numbers over here decreased, the steepness of my graph also decreased. It became flatter to where it's almost totally flat over here. Okay. Next question. Again, guys, I noticed here, this is scribble if you want to write this down, but I'm showing you how the steepness here compared to the steepness here, this one is flatter over here. Okay. So as it went down, each of these little sections got flatter and flatter. All right, question 5. Let's go on. So we got Monica. Monica takes a GPS. Guys, that's like our Google Maps on our phones. I don't know if you remember the days that we had GPS units in our car. I think now, if the cars have it, we call it built-in navigation. Okay. So with this, Monica is doing a hot air balloon ride. Okay, she's going to be watching the mountains out here in the distance. And as she gets higher and higher, she wants to pay attention to how far she is from the mountains. So let's look at this. So she's got this fancy little graph here. She made this table that told her when she was 8 feet, 8 feet from the mountains, like her distance off from the mountains. It looks like they actually have their graph backwards here. We have the balloon height as 8 and 10. Oh, never mind. I'm just reading numbers wrong. We're good, guys. So when she was 10 kilometers from the mountain, it showed that she was about 8 meters off the ground. When she was about 20 kilometers from the mountain, she was about 32 meters off the ground. I really hate that they do this in kilometers and meters because we're in the US. We use miles and feet and things like that. But anyways, let's look at this question. So when she measures the information, we get this data. So we went ahead here and our graph matches the one that they've got on our computer screen. Okay, what are some things that we notice? Okay, what are some things that we notice? Again, guys, I noticed that this is a curve. Okay, this is a curve. That means it's not constant. Just by the looks, it's not a straight line. It's curved, which means it is not constant. Okay, so now we're going to find the differences between the height and the differences in the table. The differences in the height and the differences in the table. And we're going to mark them. Okay. So what I want to talk about, these are what we're going to call first differences. We've been finding them. This is nothing different. Whenever we're taking the first row and number and finding the differences, so meaning we're seeing the change between them, this is what we call the first differences. Okay. So with this, we see that my first differences from the distance from the mountain, 10 to 20, 20 to 30, 30 to 40, it's all 10. We call those the first differences. Okay. And when we do the other ones, these are still, guys, this is also considered first differences. It's the first change, the first subtraction of this line. Okay. It's just a different thing we're comparing. Okay. So up here is our first difference of the distance. Down here is our first difference of the height. Okay. What are some things that we notice? What I notice is that my distance from the mountain is constant, but my differences in the height are not constant. Okay. The changes from one value to the next increases. So not only is it increasing in height, but from each change, it increases a 24-foot change to a 40-foot change to a 56-foot change. Sorry, meters, not feet. But you get the picture. As the height increases, the change also increases. Okay. So again, the distance from the top of the mountain are constant. My height is not constant, and it changes from one value to the next, increasing as the distance from the top increases. So again, guys, what pattern do we see when we look at the first differences? Again, I noticed that they're constant. Okay. The distance from the mountaintop was steady. It increased. And then with my balloon height, that increased at an increasing number. Again, what we just set up here. That question kind of repeats itself. Okay. So let's go ahead and look at question 9 now. Now, question 9 is going to talk about second differences. Okay. So they just showed you on the graph here. When we take our first differences and then subtract those, so 40, from 24 to 40, it increases by 16. From 40 to 56, it increases by 16. From 56 to 72 by 16, and so on and so forth. Those are what we call the second difference. Again, my second difference is going to be the difference between consecutive, that means in a row, first differences. Okay, so again, the difference between my first differences from 24 to 40 to 56, 72, 88 to 104, each of those differences are considered a second difference. Okay, what do we notice about the second difference on all of these? Okay, what do we notice about the second difference? Okay, the one thing I notice here, guys, is that my second differences are all the same. They're all the same. Okay, each of my first differences, they go up. But my second difference, they are all the same. Second differences are all equal. Okay, if we find the ratio of each of this first one, it's 16 over 10. Remember, our top ones are 10, which can be reduced to 8 over 5. We can do that for any of these. We can take them back to each one and we'd still get the same thing. They're same each time, which means that our second differences are constant. Okay. And what this models, ladies and gentlemen, it models what we call the quadratic function. The quadratic function, and that formula is y equals ax squared plus bx plus c, where a, b, and c are numbers. So like an example of this equation would be something like y equals 2x squared plus 3x plus 6. Okay, that's an example of it. Okay, the shape this graph may take may be up like this. It makes either a U shape or an N shape. Those are the two shapes that this graph can take. It's one or the other. Okay, so now we're going to take a look at another example, another type of non-constant graph. Okay, so we're going to talk about rectangle. How many of us have sat and folded notes and folded a piece of paper into little rectangles? Okay, Well, so we went ahead and we made this table. If I don't have, if I don't fold the paper at all, that's like this paper right here. If I don't fold it at all, it's one giant rectangle. If I fold it in half, I now have two rectangles, okay? And they're saying if we fold this thing up to 5 times, I'm gonna end up with 32 rectangles. So let's go ahead and graph this data here, okay? When I look at this, let me change my graph here. Okay, I said 0 folds gives me about 1. 1 fold gives me 2 rectangles. 2 folds give me 4. 3 folds gives me 8. 4 folds gives me 16. And 5 folds give me 32. What do I notice about it? That it is nonlinear. Again, guys, it's curved. It's curved. It is non-constant. Okay. So with this, let's look at question number 13. Question 13. Okay. So using that table that we just had of our rectangles, we're going to go ahead and find the first differences of the number of folds, the first differences of the number of folds. So here from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, it's all increasing by 1. Okay. So now let's find the number of first folds of the rectangles. Okay. So in the first, from 1 to 2, it's 1. From 2 to 4, it's 2. From 4 to 8, it's 4. From 8 to 16, it's 8. And from 16 to 32, it's 16. What do we notice about that? Not constant. Let's see what happens if we calculate the second difference. So now I'm going to find the change here. From 1 to 2, it was 1. From 2 to 4, it goes up by 2. From 4 to 8, it goes up by 4. And from 8 to 16, it goes up by 8. It's doubling. 1 to 2, 2 to 4, 4 to 8, 8 to 16. That's doubling. From 1 to 2, 2 to 4, 4 to 8. That's doubling. Okay. They are not constant. Okay. Neither of these are constant, and they're following a doubling pattern. Okay. When we're talking about what kind of graph this could be, this is what we call exponential. And that equation is y equals b to the x. Little hint here, guys, b cannot be the number 1. Okay. But an example of this would be like y equals 2 to the x power. We could have y equals 5 to the negative to the x power. Okay. The b is what gets replaced by a number. The y and the x are permanent in the problem. Okay. In this type of graph, this is going to be something that looks like either like that, or it's going to look like that. Okay. So now on this next page, guys, they want us to look at all these different types of data. Okay. And we're going to decide what type of graph it is. We're going to skip this because I already walked through that. And we're going to skip this next page because I already said that. All right, this last one. So we got a whole bunch of different tables here, and I want to know what types of data. Well, real quick, I just want to recap with you. Let's talk about these different types of data. Okay. I'm going to start with the most basic here, the most basic type of data. Okay. My most basic type, my linear. My linear. This is our straight line. Okay. Both first differences are constant. We are constant on both sides of the table. Okay. We're constant on both sides of the table. My y's are constant and my x's are constant. Okay. The next thing we talked about was inverse. Okay. The next one we talked about was inverse. Okay. in which here we said our x times our y's are constant. Okay, so if I had the point 3 comma 4 in a table, my next point, which equaled 12, my next point, if I had a 6 here, it would be a 2. They both have to equal 12. 3 times 4 equals 12. 6 times 2 equals 12. Okay. The next one we talked about was quadratic. Okay. My quadratic, this is where my x's were constant. My y's, we took the second difference. Second difference was constant. Okay. And then lastly, my exponential. Okay, exponential here. This is where neither of them were really constant. If we wanted to, we could say our x's are constant, but it's not guaranteed. Okay, my x's don't have to be constant, but my y's, what happens is that my y's double. My y's, the difference doubles. Okay, so let's go ahead and look at this on my chart here. Maybe I can even use my little pen. Here we go. Okay, we're going to use pink. So the difference between my 1 and my 2 is 1. 2 and 3 is 1. 3 and 4 is 1. All right, well, my x's are constant here. So we're doing good. Let's go take a look at my y's. From -3 to 0, it goes up 3. That should say a +3. From 0 to 5, it goes up by 5. And from 5 to 12, it goes up by 7. I'm not seeing anything yet. So let's start let's find a next difference. From 3 to 5, it increases by 2. And from 5 to 7, it increases by 2. So here we see second differences are constant, which means that this is quadratic. Okay, that's what we said right here. We said that the second differences are constant. Okay, I'm going to go ahead and clear that. And let's go look at my next table here. Again, I see it goes up 1, 1, 1 each time. So if it helps, go ahead and write it. Up by 1, up by 1, up by 1. Okay, now let's look at this side. I see it goes up by 4. It goes up by 4. It goes up by 4. So both my x's and my y's are constant. Well, that's what we said right up here. My x's and my y's are constant. That is linear. Okay, so my second one is going to be linear. All right, looking at my next table here. From 1 to 2, it's 1, 1, 1. All right, what's happening over here with my y's? I've got 4. I've got 8. And I've got 16. Okay, well, my x's are constant. I'm not seeing anything with my y's yet, so let's do these second differences. Let's do my second differences. So from 4 to 8, it goes up by 4. And from 8 to 16, it goes up by 8. Do you see how that doubles? From 4 plus 4 is 8. 8 plus 8 is 16. 4 plus 4 is 8. It's doubling. Okay, when we said it doubles, our y, the difference doubles, that means it's exponential. So I'm going to go ahead and drag that exponential over here, and I'm going to go ahead and erase what I have. Oops, and clear this off. Okay, now let's take a look at this next one here. From 1 to 3, it goes up by 1. From 3 to 4, it goes up. Oh, sorry. Hold on. Let's back that up a second here. Okay. From 1 to 3, that's an increase of 2. From 3 to 1, sorry, from 3 to 4, that's a 1. And from 4 to 6, that goes up by 2. All right, so I don't have constant x's here, but that's okay. Let's just check our y's. From 12 to 4, it goes down by 8. From 4 to 3, it goes down by 1. And from 3 to 2, it goes down by 1. All right, guys, I don't have anything really going on here. Well, let's check my ratio. 1 and negative 1 equals negative 1. And negative 1 and 2 equals negative 1 over 2. But then up here, I've got negative 8 over 2, which equals negative 4. I don't have anything constant here, okay? So last thing that we could possibly check is for my, we need to check for the inverse, okay? We're going to check for the inverse, which if you guys look over here, for my inverse, we say that x times y is constant. So with that, let's go ahead and look and see if my x times y is constant. So on this first one, 1 times 12 is, 1 times 12 is 12. 3 times 4 is 12. 4 times 3 is 12. And 6 times 2 is 12. There we go. My multiplication, my product is constant. So we are going to call this an inverse. Okay, quickly going through the rest of these. It goes up by 2, 2, 2. So my x's are constant. What is happening over here with my y's? It goes up by 8. It goes up by 16. It goes up by 42. With this one, guys, that is quite a change. Okay, so I'm going to go ahead. I'm going to write this down. So here we went up by 8. We went up by 16. And we went up by 24. Okay, so what I need to do is I need to look for a second difference now. My second difference between 8 and 16, it's 8. Between 16 and 24, it's 8. So I see that my second difference is constant. Second difference constant means that we have a quadratic. And lastly, 1 to 3 to 4 to 6. Let's see what we've got here. 1 to 3 is a 2. 3 to 4 is a 1. And 4 to 6 is a 2. Okay. Well, let's come over here. 18 to 14, that's a negative 4. 14 to 12 is negative 2. And 12 to 8 is negative 4. All right, well, let's check our second differences. From negative 4 to 2, that goes plus 2. And from negative 2 to negative 4, that goes minus 2. Okay, well, oh, I forgot my middle here. Oh no, we're good. Okay, so with this, guys, I'm not seeing a constant over here. I'm not seeing a constant over here. I'm not seeing a constant second difference. We've got a plus 2 and a minus 2. Guys, that's a difference of 4. That's not constant. 1 times 18 is 18. 3 times 14 is not 18. Okay, so that takes out this. How about we check our ratios? Okay, let's go back and check our ratios here. Okay, so with this, I'm going to go ahead and get rid of my second differences. Okay, let's go ahead and do my first set, my negative 4 over 2. If I write that out, negative 4 over 2, that was this set of data here. That equals negative 2. My next set of data, I'm going to change colors here so you can see it. I've got -2 over 1. -2 over 1, that equals, again, -2. I'm not going to do this last one, but -4 divided by 2 is -2. Guys, all of these are constant, which means that it is linear. Okay. Make sure you get this filled in on your table here. And with that, we're going to work on some other stuff. Wait for your instructions from your teacher.